And before it's too late, I would like to wish all of you Selamat Hari Raya Aidilfitri for those who are celebrating. Okay, so I hope you guys are well, right? So after a week break, okay. So it is an early class on the first day of your of the second part of the semester. So I hope you will enjoy your first class, all right, after the break. Okay. First of all, I would like to update you regarding our first test. Okay, I will upload the marks, all right, shortly after the class on the Putra Plus. Okay, and then it seems like um, most of you actually didn't do the exercise well, so that's actually the highest mark is actually only 20 out of 30, and the lowest is, I think, some of you even get 7 out of 30. All right, so I hope that maybe after this I will give you more exercise so that you can prepare well for your test too. Okay, actually there are a lot of questions that you can do actually from this book, right? So every topic you have every problems to be solved. Okay, by the way, I'm going to, maybe I will try to extract that questions from the book and then going to give it to you, uh, maybe like some sort of uh, online game, something like that. But it will take some time for me, so I'll try to make it soon, all right? But that one doesn't contribute to actually the marks of the tutorial, but maybe for those who can actually score the marks, so I can give additional marks to maybe for your test 2 later, all right? Or any other marks that can fit to any other assessment, all right? So today we're going to start with next chapter, which is the chapter 10. All right. So basically, it's all about the dynamics of the rotational motion. So which you already did the lab uh, the lab experiments. I think last 3 weeks. All right. So last 3 weeks. Okay. So remember that your lab report will be due this week. So it should actually be due tonight, but I will extend it until uh, Friday. Okay, I will extend it until Friday, so you will have time later. So I will change that in the Putra Blast later. Okay, so that's some sort of announcement for now. Okay, so let's continue with the learning. Actually, I'm trying to, okay, also thanks for your feedback, all right, that you give me. I'm going to actually maybe going to give you, show you some of the problem, because most of the lecture, actually, I'm going to concentrate on the lecture, on the theory first, because it is um, it is important for you to understand about the theory, and then once you understand the theory, then you can do the you can do the exercise or the problems. Okay, but I cannot give you, actually I cannot go through with you many problems because that need to be done by yourself. Okay, but I'm going to maybe summarize some of the methods or some of the techniques that you need to use. Okay, that you can use, what sort of equation giving you specific problem. Okay, but that one we will do that together tomorrow. Okay, because that tomorrow is going to be our next tutorial, right? And then maybe, yeah, I will take some time to discuss about uh, because that actually tutorial probably is not enough questions, right? Maybe that's not enough questions for you to solve. So I'm planning to give you more questions, all right? So hope you enjoy doing it. I don't know whether you have time or not, all right? Because it's a very it's too many questions, okay? Because in the physics there are so many problems, all right? There are so many ways to ask the questions. So as long as you understand the concept, all right, or you get the right technique to solve that question, so that is already enough for you to tackle, all right, right, to tackle every questions that are given. Okay, okay, back to the topic. So now we have our chapter 10, so which is actually also related to the top, all right, and also the rotational motion of the object. Okay, this is what you're going to learn in this chapter. So you basically going to learn about the torque, angular momentum, so which already defined, right, in the during the last lab session. Okay. Okay, for example, we have here a juggler. So juggler is tossing the pin. So you can see that the pin is rotated in the mid-air. So it is in the circular motion. Okay, so we have a question here. What does it take to start a stationary object rotating or to bring a spinning object to a halt? So there must be a force, all right? There must be a force that we apply for us to make that object to be rotated. Okay, so that kind of force actually is related to the torque and also the angular momentum. Okay, so we look like we have a wrench here. So let's say you want to fix your bike, right? So you have a wrench. Okay, so you must apply the force, right? So in order to apply the force, so the force, you apply the force on the handle. Okay, so you have over there, you can see that we have a FA, right, and FB. So which one that you think that um, it is easier for you to apply the force for you to loosen the bolt? Okay, of course it is at FB. Okay, uh, the actually the longer, all right, the longer the shaft, all right, the shaft of the wrench from the axis of the rotation, it is easier for you to apply the force to rotate the bolt. Okay, so that's actually the concept of the torque. Okay, so the torque is the line of action. of a force is the line along which the force vectors lie. Okay, and then that's the meaning of the torque. Okay, and then we have the also the concept of level arm. Okay, so the level arm for a force is perpendicular. Okay, uh, is the perpendicular distance from the center. Okay, so over here you can see the example. Okay, so we have a center of the object. Okay, so we have the level of the arm. Okay, so this is the level of the arm. For example, over here, so we pull the object over here at F1, okay, and also F2 and also F3, okay, and then we have a level of arm, okay, at F1, okay, and also F2 over here. It is because this F1 and F2 are somewhat a distance from the O, alright? But for F3, okay, so your level of arms is 0 because it is pulled at the center. Okay, it is pulled at the center of the object. Okay, and then the torque of a force with respect to O is the product of the force and its level arm. Okay, so that's the torque. Okay, for example over here, okay, so F3, of course, because we multiply the level of arm. So as I said, the level of arm is 0, okay, because we don't have a distance. So of course, the torque at F3 is 0. But we have torque at F1 and F2. Okay, so at F1, so the level of arms over here, L1 times the force F1, so we get the torque 1, and also for torque 2, all right, so it is similar, so L2 times the F2, okay, except that we have this one is positive and another one is negative. Okay, so this positive or negative depends on whether the force is going to be pulled counterclockwise or clockwise direction. Okay, if it is counterclockwise, okay, so if it is counterclockwise, so you actually following the rotation of the angle counterclockwise, so it is positive. But if it is clockwise, okay, so if it is clockwise, meaning that you're going towards the negative angle, okay, so you should have the negative torque. Okay, so that's the torque. Okay, that's the definition of the torque. All right, so 3 ways to calculate the torque. So we have 3 ways. Okay, so we have torque FL. Okay, and then so this is what we just learned, right? FL, but we need to sometimes we need to extract that component, right? So we need to extract that component. For example, over here, okay, we are going to rotate this object. Okay, so we're going to rotate that to the counterclockwise direction. Okay, so we applied the force upward, right? So we applied the force upward. So this F can be extract into the component, okay, into perpendicular, okay, perpendicular and parallel to the shaft, okay. So when it is parallel, so we have F cos phi, and when it is perpendicular, we have F sin phi. So we mention here as the perpendicular component as F tangent, all right. So the L, all right, L over here. So L is the one, all right, that is, okay, that is making the on the same x-axis, all right. So for example, over here, L is defined in terms of the radius of this shaft. Okay, so we define this as R, okay, the length of this shaft. Okay, so we extract that into the component as well. So L is this one. So this is L. Okay, so L is R sin phi. Okay, so either you multiply this, all right? So L multiplied with F, okay, so like that, L multiplied with F, or you multiply the R, okay, the R with the F sin phi, okay, and F sin phi is equals to F tangent times R. Okay, so that's the way you can calculate the torque. Okay, so the torque can be expressed as a vector using the vector product. Okay, if you curl the fingers of your right hand in the direction of the force around the rotation axis, okay, so your outstretched thumb points in the direction of the torque vector. Okay, one more point. So your torque, okay, back to previous slide. Okay, since the motion, okay, motion is counterclockwise, so you use your right hand, okay, and then point out the thumb, okay. So now the torque in this problem is out of the page, okay. So it is out of the page, okay. But in this problem, okay, so we are going to rotate the bolt, okay. So the torque is upward, okay. So the torque is upward. So over here, the F, the force is actually going to be, okay, out of the page and inside the page. Right, so that's the force we applied. So that's the actually the relationship of the torque F and also R, which is the length of the shaft. Okay. So let's have a look at the example over here. So we have a calculation on how to find the torque.
Attempting to loosen a pipe fitting using a winch as shown in the diagram. He's extended the handle of the wrench by sliding a pipe over the end of it and now has a total length of 0.8 meters. The The wrench makes an angle of 19 degrees above the horizontal, and the entire weight of the polymer is applied to the end of the wrench as shown with a force of 900 newtons straight down. And we'd like to calculate the torque about this axis of rotation at the pipe fitting. Well, if we draw a free body diagram of the system, here's our axis of rotation. And again, it's 0.8 meters directly from the axis of rotation to where the force acts. And we can do one of two things to calculate the torque. One is take the entire force acting on the end of the pipe and multiply it by the perpendicular distance, which is the distance obtained by drawing an infinite dotted line through the force, shown here, then taking my pen at the axis of rotation and hitting that line such that it intersects the dotted line at a right angle, as shown. In this case, the perpendicular distance is simply this L as shown. So the torque is obtained by simply multiplying the full force, 900 newtons, by this distance L, which here is written as R sine phi. Phi is 190 degrees. This is equivalent to writing it as sine cosine, 0.8 meters times the cosine of 19 degrees, which is 0.76 meters. The torque is F times L, as I said, and that gives us 680 Newton meters, and this should be positive because the sense of rotation is counterclockwise.
Okay.
The other method is to calculate the tangential component of the force. In other words, the component of the force that's at a right angle to this line.
So
I can see that
over
this
this
is
one,
going to be 19 degrees also.
so as you can see that,
and so that's going to be 900 times the cosine of 19 is 851. Now the torque is the tangential force times the total length, which is 0.8, which gives me the same 680 meters.
alright, the thing is over here, so we are given the force going downwards, alright. So what we need to find is, so it's basically it's simple. Either we find the F tangent or we use this F. Okay, either we want to use this F or we want to find the F tangent times this L, or we want to find the component of this L times the force. So it's either two ways to find the torque. So it is easy. So in this solution, okay, so of course your torque will be out of the page. Alright, so the torque will be out of you use the right hand rule. Okay, so in this solution is actually we are using, okay, we are either using first, in the first solution, it use the component of this L, alright. So initially it is 0.8, so you use that component over here. So 0.8 times sine 109. So because you need to take the angle, okay, from the x-axis to the negative x-axis. So that's why you have the sine 109, okay. Or you can also use the other angle, all right. But you need to find out. So using the cos, all right. You're using the cos, then you will get the component of the L, and then times F, so you get the torque. Okay, so that's the first way to solve it. Okay, the second way, if you need to find, you remain the L, okay, so your L is 0.8, you times the F tangential. Okay, so for F tangential, you need to find, okay, so you need to find the component, okay, the component of the F, okay, at the, over here it is 19 degree, okay, so it is 19 degree. Okay, so it will give you the same answer, okay, for both. as you can see, both solution give you 680 Newton meter. Okay, so that's how you find out the torque. Okay, and then we have the concept of angular acceleration as well. Okay, so this concept, when we have this angular acceleration, so we apply with the Newton's second law. Okay, so we have the total torque, okay, is equals to I. So we are introduced with the I here. So I is the moment of inertia. Okay, moment of inertia of a rigid body, okay, about the z-axis times the angular acceleration. Okay, so why z-axis? Because we actually, if we look at the screwdriver over there, so when we apply that rotation on the x-axis, okay, and x and y-axis, so we have the torque out of the page. So we define that as z. Okay, so this is the act of, let's say for example, we try to tighten the screw using the screwdriver. Okay, so we have a question here. Why only external torques affect a rigid body rotation? Okay, so for example over here, so we have any two particles in the object exert equal and opposite force on each other. So that's why we have the only external torque that affect the rigid body rotation. When we, as you try to screw something, okay, you feel that the force that you apply to actually to the counterclockwise direction, okay, when you try to untighten the screw, okay, when you try to untighten the screw, then actually you don't feel so much force to be applied, right, except at the beginning. Okay, so that actually relates with the moment of inertia at the initial moment, and then after that you have a angular acceleration that relates with that. Okay. All right, so we need to look at next. Okay, so we have the problem solving strategy for the rotational dynamics. Okay, for this is how you need to use this equation, all right, to solve the problem. Okay, so you can read this one. I'm going straight to the next topic, okay, because this one is actually just mentioned on how you can use these steps to solve the problems that relate with the torque and also the moment of inertia. Okay, so let's have a look at the, if we have a moving axis, all right? So over here we have a moving axis. So let's say in the first slide that I show you, first few slide that I show you, so we have a juggler, okay, tossing a pin, okay. So we have the motion, okay, of this, okay, of this spin is tossed, okay, it is combination of kinetic energy, okay, because it moves, okay, this axis of rotation, okay, is moving, okay. So because the center of this spin is actually at the middle of this pin. All right. So we move this object around, and then at the same time, okay, this object is also moves. Okay, is also moves in the direction as well. Okay. So for example here, it is inverted. Okay. You can see that this yellow, okay, this yellow ball, okay, is actually from this side, okay, from the right side is moving towards the left side, okay, when we rotate it, okay, when we rotate it. So over here, okay, the kinetic energy of this object can be defined by this equation. It is half mv squared, okay. So we just don't have the half mv squared, but we need to plus half I omega squared, okay, half I omega squared, so which is related to the top as well, okay. So but over here, we define it in terms of moment of inertia and also the angular rotation. Okay, so over here, the motion of this pin is actually combination of the kinetic energy, okay, motion of this, okay, kinetic energy, okay, motion of this object, okay, and then the translation of the center of the mass over here, which is related to the top, okay. So that's how we obtain this equation, okay. So that is how we obtain this equation. All right, we have another example. Okay, let's say we are rotating an object, okay. Let's say this is a wheel, okay, this is can be a car wheel, okay. So if this is a car wheel, then the motion of this wheel is the sum of the translational motion of the center of mass plus the rotational motion of the wheel around the center of the mass, okay. So we have the equation of this V, okay. So this the V is the velocity of this object is equals to R omega, okay. So R is the rotational motion, okay. R is the rotational motion times the angular, the acceleration, okay. So that's how we relate the torque for different object, okay, with the moving rigid body, okay. So we have this, okay, we have this kind of problem, okay, and also we have this kind of problem as well. So this is actually the combination, okay, translational motion, okay, translational motion, and also the rotational motion. So it is actually the rotational motion, okay. So this rotational motion, Okay, and then translational is mean that the object is moving. So that's meaning of the translational. Rotation is the moving of object while keeping the center of the center of the mass, right? So for example over here, so this object is rotated, right? So it is rotated to the clockwise direction, and we have the center of the mass over here. So for example, okay, I have this cup, all right? So this is the center of the mass over here. So I rotate this. So it is, we call that this is a rotation, right? So this is a rotation. But if this object is moving, okay, like that, so your translational motion is towards the x-axis, right? And at the same time, you have the rotational motion to the clockwise direction. Okay, so that's the meaning of rotational and the translational motion. Okay, so this is more example. So for example, we have the airflow around the wing of maple seed. Okay, so this is, if we have maple seed is actually going down, it is falling. So it's actually doing the rotation and also the translational. So the translational is going down, rotation is moving to the out of the page and also inside the page. And also this one, we have this car. Over here, this is a special case, right? This actually in a drag race, okay, over here V is not equals to R omega because we have, okay, we have the tire slipping on the road, meaning that at a certain moment, okay, on the drag race, the object is only having the rotational motion, but it is not having the translational motion. Okay, so mean that it is not moving to a certain direction. Okay, because it is just rotating at a similar place. Okay, so this is a special case where we call rolling with slipping. So over here, V, the velocity is not equal to RW. Okay, so we also have the combined translation and rotation. So as we learn, so when we have the combination of translation and rotation, so the acceleration of the center of the mass is equals to the total external force, right? So which is related to MA, okay? And then we also have the rotational motion, okay? So when we have the rotational motion, so we use this equation, okay? So that's the combination of the translational and rotational motion. So actually we can calculate two different force. Okay, the force that move the object, okay, to either x-axis, y-axis, okay, or z-axis, and the other one, it is in terms of clockwise or counterclockwise direction. Okay, so hope you clear with that. Okay, so we also have the concept of rolling friction. Okay, we can ignore the rolling friction, okay, if both the rolling object and the surface over which it rolls are perfectly rigid. Okay, so if the rolling object and the surface are perfectly rigid, okay, so we can ignore the rolling friction. If the surface or the rolling object deforms, okay, mechanical energy can be lost, okay, slowing the motion. Okay, for example, over here, so as you can see, we have a bump, a little bump over here. Okay, that's actually not a smooth surface. So when we have a bump over here, it's actually we slow down. Okay, so it will slow down the motion of this object. Okay, it will slow down the motion of this object. So over here, the mechanical energy is lost. Okay, which cause the object to slow down. Okay, after it hits a bump. Okay, let's have a look for another example over here.
So in example 10.7, we consider a bowling ball that rolls without slipping down a ramp. The ramp is inclined at an angle beta respect to the horizontal, and we'd like to calculate the ball's acceleration and the magnitude of frictional force on the ball. We'll simply treat the bowling ball as a solid sphere. Here's a schematic of the motion. Here's my inclined surface. And what I'd like to first do is just draw in the forces that are acting on the ball. Obviously, gravity pulls straight down. There's mg. There must be a normal force that acts at a right angle to the surface. There's n. And something must cause the bowling ball to, in fact, rotate in that direction as it rolls down. And so I'm going to need some angular acceleration in the problem. And that's going to come from a torque caused by the frictional force which pulls up the ramp from the perimeter of the bowling ball. I'll just call it F. This is, in fact, a static friction force. So here's the free body diagram of the bowling ball. The normal force again up. I'm choosing my coordinate system where down the incline is the positive x-axis. And here's the gravitational force. And right here is a static friction force, which is pulling up.
Okay, you look over here that this is the free body again. It's like in your test one, all right? So you have the normal force and then you have the friction force, okay, to the right, okay, and then you have the weight, okay. But this weight you can divide it in terms of two components, all right? So mg cos beta and also mg sine beta. Okay, so this is what you're going to use for calculating the translational motion. Okay, and at the same time, so this is the real phenomenon when you playing the bowling. All right, so the bowling ball is rotated, okay, with the rotational motion and also the translational motion. Okay, so okay, let's continue.
Now what I want to do is apply Newton's second law for the translational motion and Newton's second law for the rotational motion. To do that, First, recognize that the center of mass of the sphere is 2/5 mr squared, and it's rolling motion. So the acceleration of center mass is related to the angular acceleration by a is equal to r times alpha z, which are both positive. So the sense of rotation is positive, and the sense of acceleration is positive. So there's no relative minus sign in this equation. So I come up here and I write down Newton's second law in the x direction, and because down the incline is positive, the component of gravity down the incline is really this piece of gravity here.
Okay, all right. For this one, so you have the moment of inertia, right? So the moment of inertia, this is what you already learned in the previous chapter, chapter 9. So it is different for different object. So for example, this is a sphere. So you define as 2/5 mr squared. Okay, 2/5 mr squared. Okay, and then the acceleration. Okay, so the acceleration is equals to r, okay, times the angular to the angular momentum. All right, times the angular momentum.
And here's the hypotenuse, so it's going to be mg times the sine of beta shown here. This is the frictional force, which is up the incline. And I could, if I wish, to put an S on here, so agree with this diagram. This is starting friction force.
Okay, to find the acceleration, so which is F, okay, the total force, okay, equals to ma. All right, so we need to use this equation. So first we need to look for what is our total force. Okay, so our total force, okay, to the x direction, okay, it is mg sine beta minus friction. Okay, so that is our total force, and then you need to equate this to the ma, right? So you need to find what is this a. Okay, so your a is equals to mg sine beta minus friction divided with m. So you obtain the acceleration. Okay, so that's your translational motion. Okay, so that's the first part.
The mass times the acceleration. Here's Newton's second law for rotation. The torque is positive because the sense of rotation is positive. Here's the moment of inertia of the sphere, and here's its angular acceleration. Now I can replace alpha c by ACM over R from this equation, put it in, and I get some cancellation of one of these R's. I notice here I get another cancellation of R, and I find that the frictional force has to be equal to 2/5 times m times the acceleration of the center of mass. So I can now take this expression for F and plug it in right here and solve for the center of mass acceleration, and I get this expression. Once I have that, I can plug it back into this equation and find the frictional force. Now, if I look at these solutions, I notice
so over
if
here,
the bowling ball didn't rotate,
all right. So the problem is that
and it slid down, then I would expect
we need to
A,
find, okay,
would simply be equal to G.
what is A, okay, what is A, and also what is this Fs, the friction. Okay, so basically we know M, okay, sorry, so M is not given. Okay, so we need to find out, we need to relate, okay, we need to relate the translational force with the translational motion with the rotational motion. Okay, so it is related with So the top, okay, so the top is related with the I alpha z, okay, I alpha z, okay. So I is defined by 2/5 mr squared, okay, so times alpha z, so you obtain that one, okay. And then this is equals, okay, this is equals to fr, okay, that is equals to fr. So this fr, okay, so which is the force, okay, which is your what we call that, the friction force, okay, the frictional force, okay, because it's going to that side, okay. So times r, okay, which is, okay, which is the radius of the ball, okay, which is the radius of the ball, okay. And then yf times r, as you can see that, as we learn that um the top, okay, the top is moving, is actually out of the page, so r needs to times f, so it is perpendicular, okay, it is perpendicular, okay, r times f, okay. So are you clear with that? Okay, so r must be perpendicular to f, so we can only find the top, okay. So when we replace this, fr, okay, equals to 2/5 mr squared alpha z, okay. And then this alpha z, okay, this alpha z can be replaced with this equation, okay, can be replaced with this equation. So we replace a over here, a equals to r alpha, okay. So alpha over here is equals to a over r, okay. So that's why we have over here 2/5 m r a, okay. And then this is equals to f r. So over here we have both r on the left side and also right side, so we can cross r, and then we obtain f equals to 2/5 m a. Okay, so basically we have uh, two equations. So we to solve this simultaneous equation to find what is A and also what is F. Okay, so either you replace F first or you replace A first from this equation to that equation. So for example, you replace F, okay, so F is equals to over 5 M A, okay. So you put this 2/5 MA to this F, okay. So of course, MA minus 2/5 MA, so you get 3/5 MA, and then you can cross M, okay. You can cross M, and then this one you can sorry, it is sorry, it is minus over here, then you put over there is positive. Okay, this positive, so you need to add, okay, MA plus 2 over 5 MA, so it will be 7 over 5 MA. All right, so you cross M, and then this G sine B, G sine beta over 7, okay, times 5. Okay, so that's how you obtain your A. Okay, once you obtain your A, so you plug in, okay, your A over here, 5 over 7 G sine beta. So you place in this equation. Now you can obtain your F. Okay, so if you have any concern with this question, let me know. Okay, so basically you combine both translational motion and also the rotational motion to find what is your A and what is also your F. Okay. All right. Okay, we also have the concept of the work in the rotational motion. Okay, so to find the work is actually we need to integrate torque. Okay, we need to integrate the torque over the d theta. All right. So we have the F tangential. Okay. So R. So we need to integrate the torque. So we need to define from which angle to which angle the work is done. Okay. For example, this child is moving on this stuff. All right. So let's say she moves from here. Okay. From R1, I define this R1 to, let's say, to somewhere over here. So to find the work, so you need to find what is your torque over there, and also torque at every moment of that until that location. Okay, so that's basically why you need to find the integration of that. So you need to integrate all of that until you get the work, right? So there is a problem on this, but you will need to solve it later. All right. So basically, so this is the definition of the work in the rotational motion. And also we have the concept of power. Okay. So the power, okay, is the torque times the angular velocity. Angular velocity of the rigid body of the axis. Okay. So that's the power. Okay, for example, we have a helicopter. When the helicopter main rotor is spinning at a constant rate, okay, a positive work is done on the rotor by the engine, and negative work is done on it by the air resistance. Okay, so you know that the helicopter have the rotor, okay, at the top of the body. All right. So this rotor, I mean the its fan, okay, is moving. Okay, let's say it's moving, okay, to the counterclockwise direction. Okay, of course the torque is going to be upward. Okay, so the torque is going to be upward. So that's why this helicopter can move upward. Okay, because we have the pulling force upward. Okay, so over here, he said that the work done by the rotor is positive. Okay, so because the work, okay, the work is going to be, okay, upward, okay, following the top movement. All right, and the negative work is done by the air resistance. So you have the air resistance, so it's going downward. Okay, so it's positive and also negative. Okay, so when you just have the rotor moving, okay, so when you just have the rotor moving, so the helicopter can just go up and down. Okay, but how to move? Okay, so you know that the helicopter must also have the translational motion, okay, to move from one place to another place. Okay, so the rotor on the head of it is just to move it upward, okay, or going to be downward, right? And then you have another rotor over here. Okay, you have this rotor, okay, to move upward and also downward. Okay, and we have another rotor over here to move to that direction and then also to that direction. Okay, so that's why the helicopter can go up and move. All right, so that's the concept of the translational motion and rotational motion on the helicopter. Okay, so we already introduced with the angular momentum. Okay, now we want to define more about the angular momentum. Okay, so let's say we have a rigid body, okay, rotating with angular speed omega. Okay, so to find the angular momentum, we consider that we have the thin slice of the object. Okay, we have thin slice of the object. Okay, each particle in the slice with mass mi, okay, has angular momentum. So angular momentum, we define it as L. It is equals to m mi, okay, m of that slice, okay, times r. Okay, r is, let's say, like the length of the shaft as before. Okay, the where we rotate the object. Okay, r squared and omega, okay, times the angular speed. Angular speed. Okay, that's the omega. Okay, so that's how we define the angular momentum. Okay, for example, over here, the Li, okay, is perpendicular to the plane of motion, okay, and has the magnitude of Li, Mi, Vi, Ri. So where the Vi, okay, where the Vi is R omega, okay, the Vi is R omega, okay, times this, and then times this, and then times the mass. Okay, so before this, we have the top. Okay, we have the top. Okay, you remember that the top is the, you multiply V, okay, I with Ri. Okay, over here you have the mass. Okay, so now you have the mass, so now it becomes L, which is the angular momentum. So basically, L divided with mass is equals to the torque. Okay, the angular momentum for a rigid body is equals to I omega. Okay, I omega. So which is, okay, also relate with the torque, okay, is dl over dt. Okay, so it is the sum of all forces acting on the particles, right? It is the sum of all of that relate to with the particles. But if we have the concept of over here, the slice, so over here we divide with m, okay, the slice of the mass, okay, because we are considered so many mass, so we need to multiply with that. But in terms of the time, okay, in terms of the time, okay, we relate that t is equals to dl over dt, okay, which is the rate of the change of the angular momentum, which is the torque, right? So that's the relationship between angular momentum and the torque. Okay, and then we have the torque, okay, and the angular momentum is actually equals to the direction of the torque. Okay, it is equals to the direction of the torque. Okay, and then the angular momentum, okay, of a rigid body rotating about the symmetry axis parallel to the angular velocity given by, okay, L I omega. All right, so you have that equation. All right, so we have also the concept of conservation of angular momentum. So when we have the net external torque acting on a system is 0, okay, the total angular momentum of the system is constant. Okay, so mean that we have the net torque. Okay, for example over here, so we have a professor over here, okay, is actually holding, okay, a dumbbell, okay. So you know that this dumbbell will be rotated when we rotate this, okay. So what we have over here, okay, the torque of the dumbbell, okay, the torque of the dumbbell is acting, okay, in this system is 0, okay, because this because this actually give you the torque as well, okay, upwards, okay, and then from the dumbbell, okay, is going downward, okay. So this, when this cancels out, right, so there is no torque on the system. So let's have a look at the video over here.
All right, here I am sitting on a stool, which is free to rotate, and I'm holding two heavy bean bags. In this experiment, I'm going to start myself rotating, and then I'm going to drop the bean bags at my side. The question is, what will happen to my speed? Will I spin faster? Will I slow down? Or will I spin at the same speed?
Okay, so what will happen? All right, so what's your answer? So who choose A? Okay, you may raise your hand. Okay, nobody choose A. Okay, A, anyone? So when he drops the bag, what will happen? He will be spinning faster, or he will be spinning slower? So or his speed will stay the same. Okay, who choose B? Nobody choose B. And how about C? No one want to answer. Okay. So Shaidatul choose C. I choosing C. So let's try C.
All right, let's find out. So, as you can see, my speed did not change. This is because even though I lost some mass when I dropped the bags onto the tabletop, they carried away some of the angular momentum that I originally had. Therefore, even though I'm lighter, after I dropped the bean bags, my rotational speed remained the same.
Okay, so that's the answer, right? So the speed will remain the same. Okay, so it's similar concept for that professor. Okay. Okay, so it is similar concept with that professor. So if he throws away the dumbbell, okay, his speed will his spinning rate, okay, the angular speed will be similar. Okay, will be similar because actually the weight, okay, because the weight is not affected. Okay, the weight is not affected when you have the rotational motion. Okay, so that's why the rotational motion will be still similar. Okay, because that rotational motion actually depends on the top. Okay, so either you will be moving, okay, upwards or downwards only. Right? Okay. All right. We have cat over here. Example of the cat. Okay. It's falling down. So the falling cat twists different parts of its body in different directions so that it lands feet first. Okay. At all times during this process, the angular momentum of the cat as a whole remains zero. Okay. So over here, because it twists its body, all right? So we have the concept of the translational motion and also the rotational motion as well. Okay. So the angular momentum of this cat, okay, will remain zero. Okay. Okay, we also have the gyroscope and the precision. Okay, So the gyroscope is actually inside your smartphone, all right? So it's actually giving you the direction either to the north, okay, west, east, uh, or south, okay? So that's the function of the gyroscope, okay? So you can find out more detail about the gyroscope, you can Google it, okay? In a gyroscope, the axis of rotation change direction, okay? It is always moving, okay? That's gyroscope, okay? The motion of this axis called as the precession, okay? Precession, okay? So that's the concept of precession. The circular motion of the flywheel axis. Okay, when the flywheel, so this flywheel is rotated towards this side, okay, and also rotated to that side as well, okay. So it is like the concept our Earth and the Sun, okay. Our Earth is moving, okay, okay, and then it is also rotating around the Sun, okay. So that's the concept of gyroscope. When the flywheel and its axis are stationary, okay, okay, this flywheel, okay, this is the flywheel, and the axis are stationary, they will fall to the table surface, okay. When the flywheel spins and its axis floats in the air, okay, while moving in a circle about the pivot, okay. So what will happen is that inside our phone, right, it is always moving, okay. This flywheel is always moving, okay, towards the center of this pivot. Okay, so when it is moving, so it retains the position. It will be always floating on the air, okay. It will always be floating on the air. Because why? When this flywheel stop spinning, okay, it will drop. Okay, it will drop because whenever this this flywheel stop spinning, okay, there will be weight, okay, acting on that. Okay, there will be weight acting on that. But when it is spinning, so you have the rotational motion, okay, where you have the top, okay, and then you also have the top, okay, to that side, okay. So basically you have top to there and also top to there, okay, and then of course the combination of top will be to that direction. All right, so let's have a look. Okay, this is for example. Okay, so you have top to that direction only, okay, when, okay, this object is not rotated, okay. So you have the weight, okay, so you have the weight, okay, and then you have your top, okay, over there, okay, because this weight, okay, actually this top will be, okay, towards that, okay, will be towards, actually it is inside the paper, okay. inside the paper, all right, inside the screen. Okay, because you know that the top, okay, must be the force, all right, must be the force that is applied. Okay, the force that is applied. So where over here the force is only the weight. Okay, weight times the length over here, which is the R. Okay, so that's why you obtain, okay, so that top to inside the screen. Okay, so the angular momentum over here is 0. Okay, so as you can see over here, it says that when the flywheel is not rotating, its weight creates a top around the pivot. Okay, the top is around the pivot, causing it to fall along a circular path until its axis rests on the table space. Of course, it will fall down because the weight is acting on that. Okay, but when, okay, over here, okay, this is okay relationship between the top and also the angular momentum. Okay, so the angular momentum is 0 over here. Okay, let's have a look for the rotating wheel. Okay, so as I said, okay, so we have the top over here. Okay, so it is moving. Okay, it is moving. And then we have the angular momentum. Okay, we have angular momentum to that direction. Okay, so that's why we have a momentum over there, and then we also have the momentum over that as well. Okay, so that's why this will, okay, this flywheel will remain, okay, will remain floating on the air. Okay, back the concept of non-rotating flywheel. Okay, so in each successive time interval dt, okay, the top produce a change in the angular momentum in the same as the top. Okay, and the flywheel axis fall. Okay, so initially we have, let's say this is the pivot. Okay, so this is the view from the above. Okay, so this is the pivot, and then this is the flywheel. Okay, this is the flywheel. Okay, so you mentioned that your top is there. Okay, because your weight is inside the paper. Okay, this is your weight over there. Okay, and then you will have that length, okay, R, okay, R times that, so you obtain the top to the north. So you obtain the top to the north. So your angular momentum, okay, your angular momentum is also, okay, towards that. Okay, so your angular momentum is also towards that. So in falling, the flywheel rotates about the pivot. Okay, it rotates about the pivot. Thus, acquires an angular momentum L. Okay, so the direction of L stays constant. So your L is not moving. Over here, your L is not moving. So it just be on that direction only. Okay, it just be on that direction only. Okay, so when we have, okay, again, okay, when we have this flywheel, okay, the view from the above as well, and then it's moving, okay, it's moving. So you have L now to that direction, okay. Now L to that direction, okay, and then it will move, okay. It will move because this is the effect of the torque, okay, because your torque also going to be that direction as well, okay. Which process around the pivot, okay, as you can see, if this one, as we can see that, so we have that as this problem of the child. I relate back, okay, this one, okay, so we have the movement of the torque, okay, so we have torque moving, okay, torque, and also this moving object over there, so this is moving, okay, so basically this is what will happen, okay, so the object will move, okay, it will move, right, due to moving of this as well. So the angular momentum is not zero. When we have the angular momentum zero, then it will move. Alright? So it will move following the rotation axis of the on the pivot. Okay, over here. Alright, so you have that DL is actually moving to that. Okay, you have that DL and you have L, okay, L over there and also L over there, and so it will be like that. Okay, and then this will be continuous. All right. Okay, as we learn that the change of angular momentum, okay, so where dt, okay, of the L, okay, is perpendicular to the angular momentum. Okay, the L, okay, the value of angular momentum remains similar, okay, but the direction, okay, is moving, okay, towards the counterclockwise direction. Okay, so that's why the flywheel will be floating in the air. Okay, so that's the concept of angular momentum in the rotating flywheel for the gyroscope. Okay, so that's it for the chapter 10. Right? So that's it for now. Right? So okay, I already exceed 6 minutes. Sorry for that. Okay, so let's take a picture together for today. If you have any question later, you can ask me. So please turn on your camera. Okay, let me count from 10, 9, 8, 7, 6, 5, 4, 3, 1. Cheers. Okay, give me one more shot. Okay, thank you. All right. So have a nice day ahead. All right. So I see you again tomorrow for the tutorial. Okay. If you have any question, let me know. After this, I will upload your marks to the Putra Bus. And if you have any concern with that, let me know as well. All right. And thank you all. Okay. Assalamualaikum and bye-bye.
Thank you, sir.
Salam. Thank you,
Thank
doctor.
you.
You're welcome.